Okay. So I'm going to click on mine. Okay, so I'm doing problem number 1, and this is about the Niemann-Pick disease. And it's saying that, I don't think you can hear me now. Can you hear me? Okay. It says that 1 out of 150,000 individuals are affected in a certain population. So for 1, it's looking for the frequency of the recessive allele. So you do the square root of 1 over 150,000, which gives you 0.0026. For B, to find the frequency of the dominant allele, you do 1 minus the 0.0026, which gives you 0.9974. For C, they want you to find the frequency of the dominant D genotype, and so you do 0.9974 squared, which gives you 0.9984. So you want to find the p squared value for that. And then for D, they want you to find the heterozygous genotype. So you have to do the 2pq part of the equation. So you do 2 times 0.9974 times 0.0029, which gives you a 0.0052 for your answer.
Okay, for number 2 is fill in the blanks. The 2A says the term in Hardy-Weinberg equation that represents the frequency of IB allele is, and we put Q, while the term in the Hardy-Weinberg equation that represents the frequency of IA-IB genotype is 2PQ. For 2, it asks the 1 in 4,000 individuals in the population affected by DiGeorge syndrome is represented by Q squared, is what we put in terms of the Hardy-Weinberg equation. For C, the 3,999 and 4,000 individuals is the population unaffected by DiGeorge syndrome, and that is represented by the p squared and 2pq in the equation. D is talking about the ducks. For the answer, we put R. The R term in Hardy-Weinberg equation best represents the frequency of the MD allele. For E, we have, this question refers to the situation and presented in D. So for the ducks, we have p squared, 2pr, and 2pq. F, the human disease, sickle cell anemia, is the result of SNP. G is monomorphism. H is DEEM. And then I, we had MHC, or major histocompatibility complex.
Sorry, I was gonna sneeze. So I've got number 3, which is the Marfan syndrome. It's autosomal dominant and affects 1 in 6,000. So the frequency of the non-disease allele, all I did was the non-disease people. So 5,999 divided by 600, and I put that under the square root. So I square rooted that. And then the answer I got for that was 0.99992, because you wanted us to take it to the 5th decimal. And then for B, the frequency of the diseased allele, all I did was did minus frequency of the non-disease allele, which was 0.99992. So the disease allele frequency is 0.00008. The frequency of the heterozygotes, well, we need to do 2pq, so 2 times the frequency of the non-disease allele times the frequency of the disease allele to get the heterozygotes, which was 0.00016. And then out of a population of 5 million, how many of them are heterozygous? So we did 5 million times the number we got from C, which was 0.006, and then I got 800 individuals were affected.
All right. For problem 4, we're talking about determining, the first question is determining the allele frequencies for the R2 and R3 alleles, and it gives us the genotypes of the population and how many individuals have those genotypes in the population. So for determining the R2 allele, we do, we take 135 and times it by 2. And why we do that is because there's two R2 alleles in the 135. And then we add that by 44 because there's 44 heterozygotes and there's only one allele that has the R2 in heterozygotes. So 2 times 135 plus 44, and then we divide that by the total number of alleles in the population, which is 380, which gives us the frequency of 0.826. For the R3 frequency, we can think of the equation P plus Q equals 1. So we can rearrange that, and we can just say Q is equal to 1 minus P, or 1 minus 0.826, which gives us 0.174, which is the frequency of the R3 allele. For B, we're determining a chi-squared and seeing if it fits in our data, if the Hardy-Weinberg equilibrium is being carried out. So the first thing we do is we break this down into phenotypes. So the first phenotype I did was R2, which is also equal to P squared. And so you square 0.826 and times it by the population, which is 190, which gives you an expected value of 129.6 individuals who would have that genotype. And then you do the same thing for R2, which gives us 54.6 individuals who would have that genotype. And then R3, we would have an expected 5.8 individuals who would have that genotype. Observed, we're given those data. To determine the chi-squared, we will first do R2 again. So we take our observed of 135, minus it by our expected of 129.6, square that number, and divide it by 129.6. We do the same thing for R3, which we observe 44, minus that by 54.6, square that number, divide it by 54.6 to get our to get that next value. And the same thing with R3, we do 11 minus 5.8, square that number, divide it by 5.8. Then we add all those answers up, and we get a 6.9449 is what I got, and that's equal to x squared. That's our chi value, and that's outside of our range where we would reject the null hypothesis, and says if the population is not Hardy-Weinberg equilibrium, suggests the reason why, and we could say natural selection is occurring or different evolutionary mechanism is going on.
Okay. So is it good? Okay. It was doing that to his too. Yeah. It's better. It's back now. B is a pale gray dog, and C is an albino dog. The alleles are given from the most dominant to the most recessive. Let's assume that a particular population of these dogs is a Hardy-Weinberg equilibrium. These dogs' frequencies are. So then it gives us the frequencies of each of those alleles. Part A says, what is the frequency of a dog that has CCH? And for that one, we took the frequency given, which was 0.37, and we squared that. And we got 0.1369. And then it continues on for us to find the frequency of CBC. So we did part of Hardy-Weinberg's equation of 2 and then we times it by PQ. So we did 2 times 2.5 times 0.015, and that equaled 0.075. Then it continues, and we're supposed to find the of CC as well, and that would be 0.15 squared, and that equals 0.0225. So, and then in B, it says, among a population of 2,000 dogs, how many would you expect to have a pale gray phenotype yet be heterozygous? So, the pale gray is CB, so we know it has to have CB. So it would be CB for take 0.075 and you multiply that by 2,000. So the population, that equals 150 dogs. And then C, it says, among a population of 5,000 dogs, how many would you expect to have a white coat and dark gray phenotype yet be heterozygous? And so CD is a white dog with dark eyes. And so for that to be heterozygous, you can have 2 different alleles that are with it. So you can have CD and CB, or CD and C. So for CD-CB, you took 2 times 0.25 times 0.23 to get 0.115. And then for CD-C, you did 2 times 0.23 times 1.5 to get 0.069. And then I added those together to get 0.184, and then times that by 5,000 to get 920 dogs. And then for the last part, part D, it says, among a population of 15,000 dogs, 15,000 dogs, how many would you expect to have CHCB or CC genotypes? So to find CHCB, 2 times 0.37 times 0.25 to get 0.185, and then to find CC, we found that earlier, which was 0.0225, and then I added that with the CHCB, take 0.0225 plus 0.185, and then that equaled 0.2075, and then you multiply that by the population, which was 15,000, to get 3,113 dogs.